everybody back to our afternoon session. And our first talk is going to be by Alex Himonas, and he's going to speak about the KdV equation on the half-line with smooth and rough data. Alex, I hope you're here, and please go ahead.
Yes. Thank you very much for the invitation, the organizers. And I'm sorry that I'm not able to be with you there. In particular, because I'm going to talk about a work that was initiated there at Cambridge. But in any case, we are going to do the way we are. So let's see. Good. Here is the abstract, the collaborators. And today we're going to discuss the well-posedness of the KdV on the half-line. We were going to use the Fokas unified transform method. And this is going to be the method that this approach is based. And so we see here the KdV initial boundary value problem. The data will be in Sobolev space HS on the half line, the initial data, and the boundary data are in HS plus 1/3. This is the space suggested by the time regularity. And we shall discuss well-posedness of this problem for smooth data, meaning S bigger than 1/2 in Hadamard spaces, in analogy with the work of Kenning, Ponce-Venga 1991 for the IVP on the whole line. Also, we're going to discuss it for rough data, which is for S bigger than -3/4, which is the optimal result in the case of initial value problem. And we are going to do it in analogy of the work of Bourgain, 1993, and for S greater or equal to 0, and Kenning Ponce-Venga 1996 for S bigger than -3/4. Our data spaces are Sobolev spaces. Sobolev spaces here on the half line for the spatial variable and on an interval for the time variable. And these spaces are defined as restriction of Sobolev spaces on the whole line with the infimum norm. So just in order to be clear about the data spaces and focus in the rest on the solution spaces. Okay, so the Fokas method for studying nonlinear ibvp consists of 3 steps in analogy of the initial value problem. The first step is solving the first linear ibvp using the Fokas unified transform method. Most of the times we will call it UTM. Then using this solution formula, we derive linear estimates. And then we define an iteration map, again, using this solution, UTM solution formula, and derive appropriate multilinear estimates in good solution spaces, which gives us the well-posedness. This is the 3 steps of the initial value problem. Now we repeat them. We do the same thing for the initial boundary value problem. Again, thanks that we have a solution formula for the initial linear problem. And here is again the 3 steps in the case we are going to discuss today, the KdV. The KdV initial boundary value problem, again, we repeat here, is the problem 1. And the step 1 is solving using the UTM method the first initial boundary value problem, which is problem 2 you see here. Instead of non-linearity, we call it forcing. And then the step 2, using this formula, we're going to derive the linear estimates. And in the step 3, we are going to produce bilinear estimates in good spaces. And then we are going to do the, using them, we are going to prove contraction, the contraction of the iteration map defined via the UDM formula. We do the smooth data first. That's the way it began. In other words, we follow the story of the initial value problem. The initial value problem, as we know, first people produced optimal results just in Hadamard spaces, not using Bourgain spaces, and after that they used they went and did better via the Bourgain spaces. So here is the step 1, which is the solution of the linear KdVm ibvp, and here this is the long formula. If it was initial value problem, we would have U0 and F, and we will have only the first line here. The other 2 lines wouldn't be here because you see the other lines are because of the boundary data. So if you have not seen it before, it will require some time to absorb it, but let's, we will see it again. So here, what we see here comes in is the transform, the half-line transform of the data, which is defined here. And also we see here comes the temporal transform of the boundary data, which is defined here. And here is a mix of spatial and temporal transform on the forcing. And here the important domain that goes with the linear KdV is the D+. You see it here. It is in the upper half plane, having pi-thirds angles from both sides, symmetric with respect to y-axis. So let's just to, if there is someone has never seen this formula, let's spend a little bit time to derive it. So here is an outline of the derivation. The derivation begins, we are exploiting the exponential solutions of the adjoint equation, the homogeneous adjoint equation, and then with some manipulations we derive relation 5. So from the second order equation we get kind of first order, which is not really first order because here is another derivative inside. But in any case, we do this manipulation, and after we do this manipulation, we integrate with respect to x from 0 to infinity. And if we integrate with respect to x, then the integration will jump inside here the parentheses, and the half-line Fourier transform will be formed, and then we get relationship 6, assuming vanishing at infinity, and then integrating with respect to time, like we would solve the initial value problem for a linear equation, we arrive at the equation 7 that it's called the global relation. So here we see the Fourier transform of U, the half-line Fourier transform of U, and in this relationship we have, in addition to the G0, which we know, this is the temporal transform of the boundary data, and the U0 that we know, which is the half-line Fourier transform of the initial data, and this term, which is a mix that comes from the forcing, we have 2 unknown terms. We have the temporal transform of the derivative of the solution and the second derivative of the solution. And these need to be removed, and these are removed by deforming, thanks to analyticity of the half-line Fourier transform. In this domain, we are moving the integration over the whole line into this boundary of the domain D plus. So from 9 we go to 10, and then we exploit two symmetries. One is Xi goes to sigma Xi, and the other Xi goes to sigma Xi square. And out of the global relation, we derive two equations. And then solving the two equations for G1 tilde and G2 tilde, we remove this data, and we arrived at relation 14. And this is almost the unified transform method, except this time T here. And again, using analyticity, we replace T with a capital T. Capital T is the interval where we know the boundary data. Okay. So now that we have the solution to the forced linear ibvp, we are able to produce to estimate it in this Hadamard space. So the solution of the forced linear ibvp with initial data U0 and boundary data G0 and force in F, it's bounded by the Sobolev norm of the initial data, the Sobolev norm of the boundary data. Here is HS, but the boundary data norm is S+1/3, which comes from the time regularity known since long time ago. And then we get here this funny norm. And this norm here is funny, although it's L2, because the nonlinearity is UUX, and we don't have algebra property for this norm. We cannot produce something like this. And this is the problem of this method. And then in 1991, Koenig, Pons, and Wenger produced a subset, a new space X, which is a subset of the Hadamard space, defined via these four lambda norms. The first norm is the Hadamard norm, and there are these ones. I'm not going to take time, and if you have not seen them, you're not going to absorb them now. But in any case, this was the story in 1991. That's why this is the way that Koenig, Pons, and Wenger produced the optimal result then in Sobolev spaces without Bourgain spaces up to 3/4. So here now, in these spaces, we are producing some bilinear estimates. You see here now this funny term that appears in the linear estimate. We bound it above by the X norm of U and W. And this comes actually, which follows from this, this inequality here, which again, we're not gonna spend time. This is, I wanted mostly, this part I wanted to, it's more for, mostly for historical reasons, and also to emphasize that our approach, this is it's in analogy with IVP. And like Koenig, Pons, and Wenger struggled for the IVP till they arrived at the Bourgain. Of course, first Bourgain arrived there, using the Bourgain spaces who had the same situation here, starting with the UTM solution formula. And here is the theorem that we obtain, the 3/4. Although we are able to get for the linear problem estimate above 1/2, but for the nonlinear, we have well-posedness above 3/4, and that was the story. That's what Koenig, Pons, and Wenger in 91 were able to get using the so-called lambda norms. And here is an estimate for the lifespan, and here is here is an estimate in 26. Here is an estimate for the solution, which solution belongs to the Banach space X, which is defined via the lambda norms, and the solution is unique in this space. And also we have stability, we have Lipschitz continuity of the data to solution map. So that was the first result we were able to obtain in 2016. And now we're going to go to the rough data. And we are going to apply the same method. Again, if there is something I want to leave out of this talk, is the analogy between IVP and ibvp. And this also was why I included the earlier story about solving the KdV with smooth data. So again, here we begin, step one is the same. We produce the solution formula, the UTM solution formula using the Fokas method. And here is again the first line, which is like the initial value problem. And then we have here two more lines, which are degraded over this boundary D plus. This is a good boundary, and this is the advantage of using half-line Fourier transform, which is analytic on the lower plane. So this is again, we see one more time the solution formula for the forced linear ibvp, and now we are producing now a linear estimate using Bourgain spaces. Having this compatibility condition once S is in the time in the interval 1/2 to 3/2. So we have here again the solution, not now the Hadamard norm, but here we have the modified Bourgain norm, which you're going to see it next transparency. The modified Bourgain norm, SB alpha, restricted to R plus times 0t. This is where we get the data. Restricted there. It's bounded by now the same norms that we did it before in the smooth case of the data, initial and boundary data. But now instead of having this funny norm, we have here Bourgain norms. This is the modified Bourgain norm, temporal. This is the spatial modified Bourgain norm, and this is a temporal modified Bourgain norm that it was introduced later by a mathematician that right now escapes his name escapes my mind, but this came later. And here, alpha is above 1/2, but close to 1/2, but the B is unfortunately smaller than 1/2, which works, but requires more work in order to do it, to do the estimates. And this is again an analogy of the estimate in the smooth data case we showed before. This, you see the F now we have two sophisticated norms here, and here we have this norm that we replaced it with the so-called lambda norms. And here is the revolutionary Bourgain spaces that it's used on the whole line. This space can be used, okay, it's for any S, for any B. This is you get the Sobolev space. You have weight space in the spatial variable, the Bourgain, but here Bourgain did what people were doing pseudo-differential operators and Fourier integral operators, introduce here the symbol inside the norm, while in the linear, for linear people like Hormander and others, the using symbols in their spaces was normal, but in the nonlinear theory, I think my understanding is Bourgain was the first to introduce a weight that comes from the symbol of the linear KdV. This is the symbol. And B in the initial value problem typically is bigger than 1/2. But for the half line, we are going to use now the space, this above, but we are going to enter this one here, an extra term. Actually, this space was already introduced in 1993 by Bourgain, when he was trying to, he did there the periodic problem, and the periodic problem, the B was 1/2. And from the periodic problem, he wanted to get also the non-periodic problem, and then he used that norm. So that space is from 93. And now the alpha is bigger than 1/2 to help us in order to deal with the B, which is smaller than 1/2. Faminsky is the mathematician that I was not able to remember earlier. The temporal Bourgain norm was introduced by Faminsky, and this is S/3. You see here you replace Xi with tau, but S with S/3. And this comes from the fact that one-time derivative is equal to 3 spatial derivatives, from the fact that tau is equal to Xi cube in the linear problem. Well, now having the linear estimate, in order to having this linear estimate, here we know we are going to use having this linear estimate, we know we are going to produce the iteration map, and here the nonlinearity will come. Instead of Fs, we're going to have the nonlinearity, and then we want to show contraction, and then we have to do this bilinear estimate. And this is bilinear estimate is like the initial value problem, which holds for S bigger or minus 3/4. In this theory of harmonic analysis, that's supposed to be optimal, unless someone is willing to do things different that involve ideas of inverse scattering techniques. And I think now someone can go for the initial value problem to -1, but I don't know about the initial half-line initial value problem using this method, how low one can go. But in any case, for S bigger than -3/4, in this modifying Bourgain space, we have this estimate. In analogy with the corresponding estimate on the whole line. And this is also we have one. We need also one in temporal spaces, the ones introduced by Faminsky. There are lots of alphas and betas, and alpha primes and beta primes are involved here. I'm not expecting you to absorb this, but at least absorb that the betas are smaller than 1/2, unlike the whole line. But the alphas that help us are above 1/2, but close to 1/2. And then proving this bilinear estimate, one finds the correct values, ranges of these alphas and betas. And now here is the well-posedness. call it optimal well-posedness in analogy with the initial value problem. If we have S bigger than -3/4, then and the data belong to the correct spaces, in HS the initial, and in HS plus 1/3 the boundary data, but datum, then we get a solution in the restricted Bourgain spaces. Here, XSB alpha, satisfying this size estimate. This size estimate, the norm of the solution in the restricted modified Bourgain space is bounded by the norms of the data. And here is the lifespan estimate, and the solution is unique, and the solution to data map is better than continuous. It's Lipschitz continuous. Again, compared with the earlier result for S bigger than 1/2. We talked earlier. Now, believe it or not, one realizes the great difficulties, whatever difficulties are in the problem, by solving the simplest problem. And the simplest problem, if someone tries to produce the linear estimate, we'll start with this one. In order to have a boundary value problem, you have to have boundary data. So you have boundary data non-zero, but the initial data 0, forcing 0. And actually also we assume compact support. 0,2, we like 0,2. We could have chosen 0,3 or 0,1. In any case, having this very, very long Fokas solution formula that you saw, and we derived it. We didn't provide all the details. That was an outline. It's here now. I don't have the domain D+, but it's this domain in the upper plane from pi/3 to the other sign pi/3 on the boundary, and here is the transform. And since it's compactly supported, here we can put Fourier transform, not half-line Fourier transform here. In any case, now this is not a complicated formula, and someone has hope to estimate the modified Bourgain space. And we do actually for better, not -3/4, as bigger than -3/2. And of course, the beta here is the first time you will see you cannot do it if beta is bigger than 1/2. It has to be smaller than 1/2, and you get help from alpha. And we have this. We have the solution to this reduced pure ibvp problem in the restricted modified Bourgain norm is smaller than the usual norm of the data. Let me show you a little bit. Again, the proof is technical, but the way we do it on each ray. We estimate. We decompose it on the left ray coming down, on the right ray, the boundary going up, the blue thing, and the proofs are similar. We do only the blue one, the right, the term on the right ray, which we call it U right, and U right to decompose it to V0 now. I'm sorry, V's. Now the U is okay, we have V. I'm sorry. I think I'm talking about U, but I think here we have V. Yes, V. So we decompose this near 0 here and away from 0, near infinity. This is near 0 and near infinity. And we will estimate the modified Bourgain norm, restricted modified norm here and there. And in order to do the restricted norm, we have to extend. And using this the smooth version of absolute value x, we do extend this the solution near 0, and then we do some work, and we obtain, you see, this is a restricted norm bounded by full norm, global norm, and we get the estimate we want. Similarly, for the solution of the reduced pure ibvp near infinity, again, here we write it after some manipulations. We write it in this form, in this extended form, by using this kind of one-sided tent function like this. And then we have, in order, it suffices to do the Bourgain norm, the modified Bourgain's norm, the global norm of the here, the function here, the solution, the part of the solution described here in 52, and we get this after some work, significant work. And time is here to mention that one may say, well, and its method has its own motivation. Bona and company used the Laplace transform in time to solve the initial, the first linear ibvp, and if you do that, of course, then you are going to have for the KdV a third order, the third order of D in spatial variables. You solve it and you do what you do. This is initiated by Bona and company, but Erdogan and Zirakis also are following this in a little bit with their own spin, introducing some ideas of their own, technical ideas. And we have also the approach of Colliander and Kenning, which they do exploit the initial value problem. They don't begin from solving the initial boundary value problem. This approach, the Fokas unified transform method approach, it just spends a lot of time, lots of energy to solve the linear problem and derives the solution, and then in principle follows the ideas of the initial value problem. And that's what we were able to show, that it works, although it's more technical. And by the way, the results are the same with all three methods. I mean, in terms of optimality. Now I'm going to tell you that what I think as an advantage of this method, you can do higher order equations. And here is, I'm going to show you a higher order dispersion KdV, which includes the KdV. If you put m is equal to 3, you get KdV here. If you put m is equal to 5 here, you're going to get the Kawahara equation with alpha equal to 0. We had the talk yesterday, I think, where there was a Kawahara equation with an alpha term here. The alpha here is 1, and there is a minus sign here, good there, and just to have the same Bourgain spaces. There is no difference. You could ignore this thing here. So m is 2j plus 1. So here this is j. You see here, we have one initial data, but we have j boundary data. In the case of Kawahara equation, we will have 2 boundary data. And the Fokas method is the same. Solve the first linear problem, which here it will be more challenging because the higher order thing, and then use it to derive linear estimate, and then derive my linear estimates and and Bourgain norms will change. The dispersion is different, so the Bourgain norms, the C cube will come C to the M and follow. And this is what we do here. And here is, if you had hard time to absorb the UTM solution for the KdV, this will be even more difficult to read those symbols here, but it's beautiful if you understand the unified transform method for solving the KdV equation. You are patient, you're gonna derive this formula, and maybe you're gonna write it in a better way that we're writing here. And you're going to get not only one domain, not only one magic domain D, we're going to get J of them. This is the J on corresponds to KdV, and we get here the middle one, the one which is symmetric to the y-axis. You get only one. But in the case of Kawahara equation, we are going to get not this one, we're going to get two, this and that. Let me show you actually, I think, okay, maybe Kawahara equation comes later, I have it somewhere. Okay, here are the half-line Fourier transform is the same. The temporal Fourier transform is the same. And here are the other F transform is, yeah, analogous, the same. The M goes to 3. And here is the Bourgain spaces are precisely the ones that we talked earlier, but instead of C to the cube here, instead of C to the cube, we have C to the M. And instead of dividing by 3 here, we divide by M. Because here, one-time derivative is equal to M spatial derivatives. And yeah, here is the Kawahara story. The Kawahara story, we have 2 domains here, the D2 and D4, okay? And this is the Kawahara UTM formula. And you see also the 2 boundary data, G0 and G1. And the linear estimates for KdVm, we call it KdVm, this equation, are very analogous to the KdV equation. The optimal here we get that this minus J minus 1/2. We do better. You will see actually the well-posedness is minus 1/4 here, not minus 1/2. So I'm sorry, what did I do? Yes. Again, the UTM solution formula with one initial datum and J boundary data in restricted Bourgain norm is modifying Bourgain norm is bounded by the natural norms of the initial and boundary data, and the 2 Bourgain norms. This is the temporal Bourgain norm, modified Bourgain norm temporal, and this is this is the spatial in the space variable, and this is in the time variable again, due to Faminsky. And again, here also the B, which in the case of the line is bigger than 1/2, is smaller than 1/2, but the alpha again is bigger than 1/2. And the interesting thing, we are able to prove bilinear estimates. And the bilinear estimate is minus J plus 1/4, the spatial bilinear estimates in modifying Bourgain spaces. And in fact, this estimate, we have written a paper with collaborators, and we did this first for the initial value problem. We have a paper, I think it's 2020 paper, where we prove these estimates and the well-posedness of the initial value problem for the MKdV of the whole line, and we prove this on the whole line. And here is the temporal again, and here is not smaller than 3, smaller than m, and this is the corresponding linear estimate, which is the step, the linear estimate is here. Okay, and here is the bilinear estimate, which we are in step 3, and will help us. The bilinear estimate help us to show that the iteration map defined by the Fokas solution formula is an iteration map, which is really this theorem. That's what it says. If you have S bigger than this optimal Sobolev well-posedness index, and S jumps certain values that are known, and the data are in the correct spaces. So it says the initial data and the boundary data, the ones suggested by the time regularity. Then there is a unique solution. There is a solution in the modified Bourgain space, XSB alpha, that satisfies this this size estimate. It's restricted. Modified Bourgain norm is bounded by the norms of the data, and here we have the estimate, an estimate for the lifespan, and the solution is unique again. And the data to solution map is Lipschitz continuous. Here is the theorem for the, this is the theorem for the Kawahara equation. It's the identical theorem that we had there, but here the optimal well-posedness index is -7/4. This is the one which is in the literature. There is Kawahara equation that has here even alpha and also has some coefficients. This question about coefficients in the Kawahara equation was discussed, I think, yesterday. But if you put coefficients, you can prove more, at least for the initial value problem. That's what it is, the optimal regularity. And again, here you have the solution in the modified Bourgain spaces is bounded by the data, and you see here now the data, the G0, S2 over 5, S plus 1 over 5, and the estimate here for the lifespan, an estimate for the lifespan, and the solution is unique, and dependence is Lipschitz continuous. And by the way, my understanding of the Kawahara equation is it's not an integrable equation, and one may wonder if for the KdV, people go lower using other methods inspired by the inverse scattering. I'm talking, have in mind, at least in the non-periodic work, the work by Kilip and the second author, again, it escapes my memory. And here I would like to tell you thanks for your attention. Any questions?
Yeah.
Hello, thank you for the nice talk. Regarding the last reference, is it Kilip and Visan? Is this the paper?
Visan, yes.
Thank you.
It's Kilip and Visan.
Okay.
And then in the non-periodic case for the, again, I put myself into trouble, is Peter, who are the authors? It's Kappeler and one more guy, Topalov and Kappeler and Topalov. In the non-periodic case, they go -1, long time ago.
Hi. In equation 4, you define basically the function f that you're using the unified transform method.
Question, where did you say?
Equation 4.
Question 4. Yeah.
Yes, there. So you're assuming that this function f is general, right?
Yeah.
So have you ever thought about f being non-local in the sense of the Kamasa-Holm equation? So you have the inverse of the Helmholtz operator, for example. And what kind of difficulties would that bring?
Very, very good thing. But if you want to do the Kamasa-Holm equation this way, this is what me and Professor Michalek tried to do in 1993. When I start getting into this, the trouble with the Kamasa-Holm equation will not be this. You don't have linear, you don't have dispersion. Unfortunately, the dispersion, whatever, if there is any dispersion, it's hidden in the nonlinearity, the non-local nonlinearity. The Kamasa-Holm equation, you remember, is dt is ut plus Berger's plus the non-local thing. So what you're missing from the Kamasa-Holm equation is this guy. So the linear, if you try to do the linear UTM for the Kamasa-Holm equation, if you just do it in not smart way, you know, you have to solve, you have to get rid of UUX, and you will do the, if you write in the non-local form, yes? If you write in the non-local form, will be UT, and the other side will be all the non-linearities, and in front, some of them, they will have then the non-local thing. But might be a way, I don't know, maybe you shouldn't, I don't know, you don't write it in the local form. Did I answer your question?
Okay, are there any further questions?
Hi, Alex. Thanks for your talk. Do you think there's a way to combine the Killip-Visson method to get down to H-1 with the Fokas method? Or is there, you need fundamentally new ideas?
Of course, you will need fundamentally new ideas, but it's a nice idea, actually. If you could do, I have thought about it. This is actually, this is not, it's a recent paper. Is it 19 or 20? 2019 or 2020? Published in the Annals of Mathematics. That will be something. Because again, there is, of course, it's not relentless. There is not bilinear estimates and multilinear estimates. There are, it's somewhere in between. I have not studied the paper, but this, you know, yeah. Like when people did the optimal descent using harmonic analysis, these results for the KdV are optimal. But then Kappeler and Killip and Visson, they did progress in both directions. And actually, it took time, at least for the non-periodic problem. I remember I was on sabbatical at Chicago when I heard the talk, I don't recall who, many years ago, where, you know, it took so long time in order to for the non-periodic. The non-periodic, it's much harder. But that's a very good question.
Okay, are there any further questions? If that's not the case, then let's thank our speaker again.
Well, thank you very much.
And we have a 10 minutes break.
I were there. Bye.